how to change the subject of a formula. For example, a common electrical equation is that voltage is equal to current times resistance. There's some different ways that we can do this, and I'm going to show you a pretty straightforward method that's going to work for all of these. It's going to slowly build. We're going to start simple. We're going to get into some more complex stuff. So let's say we want to make current the subject of the formula. Okay, so we'd say we want to solve for I, or we want to make I the subject of the formula. Okay, so what are we going to do to get I alone? Well, what we can do is we can divide by R on both sides. When we divide by R on this right side here, since we have a multiply by R and a divide by R, these cancel each other out, and we no longer have R on this side. Look on the other side, and we can see that we have an E, and now that is over the R, and that is equal to I. Now we completed the formula, and it would be good to just flip it around and say I equals E over R. We can now see the subject of the formula is changed. Now leave a comment for what would be the answer if we solved for R. Okay, here's number 2, and I'm gonna link the sources for this down below. So you'll see these are from legitimate sources, so you can trust everything I'm teaching, as well as see where this information came from. Okay, so we see the formula of y equals 3x plus 4. And as you can see, we want to solve for x. In this case, we're gonna take the 4 and we're gonna move it on the other side. So in other words, we're going to do the opposite of what we see here. We see it is a positive 4 and it is adding. So we're going to take a minus 4. And on the other side, the same thing, minus 4. Again, the plus 4 and the minus 4 are going to cancel out, which will leave us now with y minus 4 equals 3x. Next, we're just going to take the 3 and put it on the other side. So we're going to do divide by 3 here. And here we have y minus 4. So instead of doing each individual one divided by 3, we're not actually going to do that. We're going to take everything and we're going to divide it by 3. So now we see y minus 4 divided by 3. Of course, the positive 3 that is multiplying now becomes still positive 3 that is dividing. And because of that, those cancel out. Now I'm going to write this starting with x on the left side. So now we see that x equals our y minus 4 over 3. And of course, you could also write that as x equals parenthesis y minus 4. And then that would be divided by 3. Okay, so either way, but this would be the more common way. And it might be a little easier to read because it is more common. So there's that final answer there. Okay, number 3, we see a equals b over 3 minus 5. In the last example, we saw some multiplication and addition, and we chose to get the addition on the other side. Okay, so same thing here. We're going to deal with our subtraction first. So we do see b divided by 3. So we do have b. Of course, I should have mentioned we're solving for b. Okay, we're solving for b. So we have plus 5 on this side, and we have plus 5 on this side. Again, the subtract by 5 and the add by 5 are going to cancel out. Now on the left side, we see an a plus 5, and that is going to equal the b over 3. And now from here, we're going to multiply by 3, and then similar thing on this side. We're going to take everything here, and we're going to multiply it by 3. Okay, so I'll actually change this to a dot 3 so it doesn't look like I'm doing a x3. So you see times 3, divide by 3, times 3, cancel out. Okay, I see the red smearing with the black, so I'm going to stop using the red. I'm just going to cancel out with black. Probably won't even matter to you. Okay, now I'm going to rewrite this with the 3 canceled out and b starting now on the left side. So now we have b equals 3 times a plus 5. Okay, and you could write it like that, and we could imagine that we're working with much more complex numbers. Maybe these are decimals, okay? And we're just rearranging everything. So at this point, when we're looking at this, we could keep this how it is. We could keep it as b equals 3 times a plus 5. Okay, but in this circumstance, in a lot of circumstances, you're going to want to do what is called expanding this. Okay, and that's simply where you just multiply what is in the front here, which is what would be happening. So we're going to take 3 times a and 3 times 5. And now that's going to give us b equals 3a plus 15 with 5 times 3. Okay, so that is the answer to this. Okay, now number 4, we see 2y equals 3 times 2 plus x. Okay, now in this circumstance, when we want to solve for x, what would we do first? What would be a good idea to do first? Okay, so we see 3 multiplying by 2 plus x. But instead of dealing with that how it is, why don't we just expand it? In other words, take the 3 and multiply it by the 2 as well as the x. So now we're just going to rewrite this as 2y equals now 6 plus 3x. Okay, so now think about what we've been doing in the other ones, and we see some multiplication on the right side where we see x. We want to isolate x. We also see some addition. So let's get rid of the addition, and by doing that, we're going to subtract by 6 because we see the 6 is, again, it's addition. 6 is adding. And again, not to overcomplicate everything, but the quality of this actual number doesn't change to where we had a positive 6 addition, and now we still have a positive 6 and subtraction. So that just doesn't change. And again, we're doing a 2y minus 6. The 6's cancel out on the right side. Now on the left side, we have 2y minus 6 now equals 3x. Okay, and now again, we want to isolate x, so you probably know what to do from here. We're going to divide by 3 on this side. It's going to cancel it out. We're going to divide by 3 on now the left side to everything there, not just each one. And you see now 2y minus 6 over 3 is going to equal x. Of course, we'll rewrite that as x equals 2y minus 6 over 3. Okay, and there's our final answer. Okay, number 5, we see 6a equals 3 plus b over 2. Solve for b. And these are starting simple. I promise they will get more complex. It will be good to watch each one chronologically because each one will slowly add some more complexity. And what we learn in each one will add another thing that we will then apply to the next ones, and they'll keep building on each other. Okay, so again, similar thing as before. We see b, and we want to isolate b. We see on the same side that b is being divided by 2, and we also see that 3 is being added to b over 2. And since we want to isolate b, well, let's get rid of something that's on the same side as it. Let's get rid of this 3. 3 is adding. Now we're going to do a minus 3. Subtract by 3. And on the other side, same thing, subtract by 3. Okay, so now on the left side, we have a 6a minus 3, and that is now equal to b over 2. Okay, now again, we want to isolate b, so we're just going to multiply by 2, and then we're going to multiply everything here on the left side, also now by 2. I'm going to rewrite the formula starting with b on the left side. Now we have b equals 2 times 6a minus 3. Okay, now again, it would be a good idea to expand this, especially with these simple numbers we're working with here. Now this formula is going to turn into b equals 12a minus 6. And that is going to be our final answer. Okay, so technically we could call these formulas. We can also call these equations, because an equation has one quantity that is equal to another quantity. They equate. It's an equation. And you could also describe it as a formula where one quantity equates to another quantity. Of course, we're using variables here, but they're all serving a placeholder for some sort of quantity. Okay, next question. We see we're tying in some physics. Density equals mass over volume. We're going to write that as D equals m over v, and we want to solve for v, which is going to be volume. Okay, so from here, what would you think would be the first choice? And you might think, well, you're just going to multiply by m. Pretty easy, right? D times m equals v. Well, you'd be incorrect. Okay, so you need to remember, do not multiply by your numerator. In other words, the top number of your fraction, or if this was m divided by v written left to right, you would not take this left number here and multiply it, because this left number's not being multiplied by anything. And you also wouldn't subtract it, because then you would have your divide by v left all by itself, and you're not just going to have d equals divide by v. That doesn't make any sense. So it wouldn't make sense to subtract it, and it also makes no sense to divide it because it's dividing into this. It's not being divided into. Okay, so because of this, we can see it's pretty obvious that v is being divided into. So because of this, we're always going to multiply by our denominator because you can see it makes sense. We have m divided by v. So to cancel this out and to move something on the other side, because as you can see the other choice didn't work, our other option is going to be to multiply by v, canceling out v on this side. Now we have volume times density, and that is equal to mass. Now you might think this is a little bit odd because we're moving the thing that we're trying to isolate on the other side, but you can see where it makes sense because process of elimination, that was basically our only choice. Okay, now, well, you can guess what we do from here. We want to isolate v. So now we're going to do divide by d. Of course, the d is going to cancel out, and we're going to have m divided by d. So now we have v equals m over d. This is our final answer where we see volume is equal to mass over density. Okay, now number 7, we see y equals 2 over 5 times x. We want to solve for x. So now remember what I said. The 2 over 5 is being multiplied by x. Okay, so we could always divide by x and get x on the other side, but that probably wouldn't do us very good. Here's a good trick if you have a fraction that you want to get rid of. We can take the reciprocal of our fraction and multiply. So we get 2 over 5. I'm going to rewrite x over here for now because what we're going to be doing is we're going to be multiplying 2 over 5 by 5 over 2. Okay, so they're reciprocal. What this is going to do is cancel out the 5 and the 2. But of course, what we do on this one side, we do to the other side. So of course, we're going to do multiplied by 5 over 2 on this left side. Okay, so now rewriting it with x on the left side, we have x equals 5 over 2 times y. And you see I just wrote it similarly to how it started. We had y equals 2 over 5x. Now we have x equals 5 over 2 y. And that is our final answer there. Okay, so now we see number 8, f equals 9 over 5 times c plus 32. This is the formula for converting Fahrenheit from Celsius, where when we have Celsius, we're going to take 9 over 5 times Celsius plus 32, which normally we would have 9 over 5 as a decimal. So it's good to know that 9 over 5 is simply just 1.8. Okay, but the point of this is that we're working with the fraction. So it's the fraction for 1.8. First, we want to solve for Celsius. Okay, so we're going to think about the same thing. We see division, multiplication, and we see also the addition. So we're going to get rid of the addition, and we're going to do minus 32 here. That'll cancel this out. We'll get minus 32 now on the left side. And now that's going to give us f minus 32 is equal to 9 over 5 times c. Okay, so now we have the fraction. We have 9 over 5, and again, just like our last one, let's instead just do the times the reciprocal. So I'll just write it over here. So we have 9 over 5 upside down. We have 5 over 9 now, and we're going to multiply this over here where the 5s are going to cancel and the 9s are going to cancel. And just to, I really like explaining things. So instead of just saying that they cancel, why do they cancel? If we think about it, 9 times 5 is 45. 5 times 9 is also 45. So all that we're going to end up with is 1. 45 over 45, that'll just cancel out into 1. So just in thinking of terms, if we did keep that around, then we'd have c times 1 on this side. So we can just get rid of that. That's why this trick works. But now on the other side, we're going to do the same thing that we did on the right side, here on the left side. Now we're going to take our f minus 32, and we're going to multiply the reciprocal of 9 over 5. So we're going to get 5 over 9 times the f minus 32. Okay, so now I'm going to rewrite it with c on the left side. Now we have c equals 5 over 9 times f minus 32. Okay. Okay, so there's our final answer. And again, 5 over 9 is a fraction, so we could always write that as a decimal, which would be 0.5 repeating. Of course, with the repeating number, to get as accurate as possible to it, when you're multiplying, let's say you had 2 times 0.5 repeating, instead of just writing 0.55 or 0.555 2 or 3 times, to get more accurate, you write as many 5s as possible. So you write 2 times 0.555555555, press enter, you're going to get closer to the answer that 0.5 repeating would actually get you. Of course, a repeating number, you're never going to get actually exactly on the money. So see, that sheds light on if we thought about, okay, well, we have this fraction, we probably wouldn't want to expand this, but what would happen if we did? And we can see, well, we're working with a repeating number as a decimal. We'd have 0.5 repeating, so that would not be very convenient to then expand this. So this is good where it is, and the fraction actually works out conveniently because it gives you the 0.5 repeating number. Next, number 9, the kinetic energy of a moving object is equal to 1/2 times the mass of the moving object times the velocity squared of that moving object. We want to find the velocity. Okay, first, it would be a good idea to get rid of this fraction. We're going to do the same thing that we've been doing before, and we're just going to multiply that fraction by the reciprocal, which will cancel this out. And of course, whenever we have 1 over something, it's just going to be that whole number. So 2 over 1 is the same thing as 2. So now we're going to have 2 times the kinetic energy, and that will equal the mass times the velocity squared. Okay, now we run into some interesting territory here, which is a very good learning lesson. Okay, so since we're solving for velocity, it'd be a good idea to get rid of the mass, the m. And we're not dealing with a fraction this time. We don't have m over v squared, we have m times v squared. So in fact, this is multiplication. As we know, multiplication and addition, they can be rearranged. So this very well is the same thing as saying v squared times m. So these two things are just multiplying together. Okay, and because of this, in this case, it actually would make perfect sense to divide this by m to get rid of the m on this side, and then we just have to go on the other side and also divide everything here on the other side by m. Okay, I'm going to write the v on the left side, so we have v squared, we still have the squared, and equals, as you can see, 2 times k e over m. Okay, now what do you do when your answer is being squared? What would be the opposite of squaring something? And that would be square rooting. Let me write that out. So I always like to explain things. So real quick lesson. You have 12 squared equals 144. This means 12 times 12 equals 144. Okay? If you got 144 your answer, and you got the square root of that, that would be 12. Okay, as you see, I canceled out the square there because I square rooted this, and it gave me the correct answer. The square root of 144 equals 12. So that's how you cancel out a square. It's just doing the opposite. Okay, so now we see that we're going to square root this. That's going to cancel out the 2. And then we're also going to get everything on the other side. Okay, and we're going to square root it. And you saw that if we're taking the answer that we're starting with and we had that squared, then we can just get rid of it by square rooting it. So now we have the whole entire other side square rooted, because now this whole entire other thing square rooted is already going to equal v, okay? So it sounds kind of complicated when you try to put it into words, but you can see when you solve for these things, it makes sense. Number 10, the acceleration of a particle equals the change in velocity over time, where in vf, the f is going to represent the final velocity, and O is going to represent the initial velocity. We want to find VF, so the final velocity. Okay, so now we could think about the other formulas we did previously and how we would get into a circumstance where we would have something subtracted by another thing, and the difference of that would be over something else. How would we get into a state like this normally? And a lot of times that would have been if we were, let's say, moving in this initial velocity from this side to this side as our first step, and then we ended up having a times t, and we ended up putting that over here for our second step. So maybe that was something that we could have done. And just thinking in that context, you could see we're thinking backwards from there, and seeing that we have vf minus vo, that total thing is divided by t. Take our first step isolating the final velocity, we can multiply our time. Okay, so it actually depends on just understanding how to do this. And this is just algebra here, okay? That's what this is. Okay, so now on the left side, we can see that we're going to have times acceleration. Something that's just a little weird about putting ta next to each other. So put the dot, and then we have equals the final velocity, of course, subtracted with the initial velocity. Now, pretty simple. We want to isolate the final velocity. So we're just going to add the initial velocity, get rid of it on this side. And now everything here on this side is going to have the initial velocity added to it. So rewriting it with the final velocity here now on the left side, we have the final velocity equaling times acceleration plus the initial velocity. And that is our final answer. Number 11. We can see things are a little more complicated. We have x minus b over 4 equals x minus a over 5. We see one thing, we see a variable on both sides, x and x. So that should catch your eye right away when looking at this. The next thing that should catch your eye right away when looking at this is that you have a fraction equal to another fraction. That can be kind of weird and awkward to think about and figure out. And you might have been already trying to think about that without actually making the connection that the problem here is that you have a fraction equal to another fraction. Okay, so that is a problem that's going to cause some difficulty. What do we do in the circumstance where we have a fraction equal to another fraction? We're going to disregard the x on both sides at the moment because, of course, we're going to be moving things around and solving things. But to make things less complicated, one method that we could do to change this into a different formula that's going to be much easier to solve is going to be with cross multiplication. And simply think when you see two fractions have an instinct to cross multiply to make an easier formula. In other words, we're going to take 5 and we're going to multiply that by x minus b. We're going to take 4, we're going to multiply that by x minus a. Okay, and both of these left and right sides equal each other, so of course they can be written either way. I chose to do 4 and then 5, but we can see that, like our other ones, it would be a good idea to expand this where we are in this situation. So in other words, we'll take 4, we'll times that by the x and the a, we'll get 5, and we'll multiply that by the x and the b. 4 times x is 4x. 4 times the a that is being subtracted from the x becomes 4a that is still being subtracted from now the 4x. This is now equal to 5x minus a 5b. Okay, now we want to solve for x, so this is a little interesting here. First off, let's look at one thing. Since we do have the same variable x and x, let's look at what we have. We have a 5x and we have a 4x. These are both in a circumstance of subtraction here, but they're not being subtracted from. Okay, they're just existing in the state in the beginning of each side of the equation that they're landing on. So it's just a 5x minus 5b. Okay, we want to keep our 5x and our 4x together because we have these two of the same variables with just different values. Okay, so let's change this into one value. So now we just have 1x. And how we could do this is getting our positive 4 and subtracting by 4x to get rid of it. And don't think about it much more than that. Okay, so now we're going to minus 4x and we're going to have 1x, which, if you think about it, 1 times variable x is just going to be x, okay? Okay, and now we still have the negative left over from before. That doesn't go away, so now we have negative 4a equals x minus 5b. Okay, now we have x at least all in one variable, and it doesn't even have a number. It's just by itself at the moment, besides having the minus 5b. So to get rid of that, we could just do plus 5b on this side, getting rid of it on the right side. Okay, now I'm going to start writing everything over here. Okay, so we got rid of the entire minus 5b. So now we're just going to start off with x equals, and with our 5b added on our left side now, we're going to start off actually on 5b minus 4a. Now you might think this is kind of weird. We didn't do negative 4a plus 5b. We just did 5b minus 4a. So you can see where algebra is kind of interesting, where you can just rearrange certain things when you know how to rearrange it. So see, the final answer is x equals 5b minus 4a. Okay, next question, 12. We see r is equal to 3x plus 4 over 5x minus 7. Now remember, this whole thing up here is divided by this whole thing down here. So to get rid of the denominator in more mathematical terms, we'll take the entire denominator there, 5x minus 7, and multiply that. First canceling it out on this side and then doing it on the next side. Okay, so now we have r times 5x minus 7 equals 3x plus 4. Now, you might be wondering, would it be a good idea to expand the r with this? And yes, it would be a good idea. So we do r times 5x and r times the subtracted 7. What that's going to give us, interestingly, is 5rx minus 7r. That's going to equal, of course, this didn't change on the right side, our 3x plus 4. Okay, now, of course, we want to isolate x, and we do have 3x. We need to comprehend one thing, is that 5rx and 5x are not the same thing, of course. Okay? Those do not equal each other. Okay, so now in this circumstance, we're going to want to get these on the same side, the 5rx and the 3x. So it won't matter which one we add to either side. In this case, we're going to get the 3x, and we're going to move this onto the left side of this equation. Okay, and how we are going to do that is we are going to subtract the 3x from this side, and then, of course, we're going to have to do that now to the next side. Okay, now we're going to get 5rx minus our 3x minus our 7r. That is going to equal the positive 4. Now, though it may not seem like it, we are trying to isolate x. So it would be a good idea in this circumstance is to add the entire 7r from the left side and getting rid of it. Now it appears here on the right side. Now we have 5rx minus our 3x equals 4 plus 7r. Okay, so now we need to comprehend something. Rx is not the same thing as x, but x is the same thing as x. So those do equal each other, okay? The significance that this has is we can factor the x out of the equation and then factor it back in to give us a different formula and to help us solve for this. Okay, so how do we do that? Okay, so let's think of removing the x. And what we're going to be left with is our 5r minus 3. Okay, and now if we want to factor the x back in this equation, we can just think about how we could get x in here. Okay, and that would be is if we expanded this equation of x times 5r minus 3. If instead of expanding it, we're going to use this to our advantage. And we're going to keep this as the formula that we're using. X times 5r minus 3 is now equal to 4 plus 7r. And now since x is multiplying this entire thing of 5r minus 3, well then we could just think about getting rid of it by dividing by the entire thing of 5r minus 3. Now we're going to get rid of it on this side, and of course we're going to add it here on the next side, giving us insight into the answer of x equals 4 plus 7r over 5r minus 3. And if you like things to look more organized, you could always write that as x equals 7r plus 4 divided by 5r minus 3. So the r's are going to line up and the plus and the minuses are going to line up. Okay, but that is our final answer there. Okay, so the next one, we're going to be thinking about parallel resistors. So this is an electrical channel. If you're used to solving for resistors in parallel already, this might seem a little bit ridiculous, but the point of this is to learn how to change the subject of a formula. So I recommend still watching this because this will be a good lesson on something you're familiar with. So basically, if you already know how to solve for parallel resistors, that's no problem for you. This will seem definitely like overkill, but we're going to see how we can translate this into much more complex topics. Okay, so this will be written maybe a little differently than you're used to, but I'll explain it how you might be used to it being explained. Okay, so we're going to have our 1 over r1 plus 1 over r2. You're normally used to seeing 1 over this as well. Okay, so we think this total, 1 over r1 plus r over 2, is then just furthermore divided by 1 again. So if we want to rewrite that, we could write that as 1 over RT equals 1 over R1 plus 1 over R2, where it's saying the sum of this on the right side equals 1 over RT. Okay, so it's a different way of basically writing something that you're used to. It makes perfect sense though. So let's say we wanted to find R1. What would be the first step? And if you think subtracting 1 over R2, then you're correct. Now we're simply going to have 1 over RT minus 1 over R2. That's going to equal 1 over R1. Okay, so now what can we do? We have 1 over R1. We want to isolate R1. And we also have everything else 1 over. It's a little bit of a unique problem here. So now to think in terms of getting rid of the 1, because the 1 is the only thing on the side with the R, we could think multiplying by -1 to both sides. That's going to get rid of our 1 here. Now I'm going to rewrite it with R1 on the left side. So now we're going to have just R1, since the 1 canceled above it, is equal to, and this is a little interesting, we're still going to have to do 1 over RT minus 1 over R2. And this is because when you're multiplying by -1, you're not multiplying -1 by each of these separate values. You're actually instead multiplying -1 by this difference of 1 over RT minus 1 over R2. That difference, so you can see where we have that here in this equation. So now we have a complex fraction. In other words, we have a fraction with some more fractions inside of it. We could simplify this by multiplying both this top and the bottom by RT and R2. Okay, so first we're going to multiply the bottom, RT times R2, and as well as the top, RT times R2. So first and foremost, what this does to the bottom is from the beginning, we have 1 over RT times our RT times R2. The RTs are going to cancel out in that situation. And now since the RTs are going to cancel out, all that's going to leave you with is the R2. So you're not still going to have the 1 over RT that is canceled out now. Instead, now you're going to have R2. Next, we go to the R2. The R2s also cancel out, and we had the RT in this equation to begin with, so we still have that left over now. So R2 is canceled out, so the whole 1 over R2 is canceled out completely. Left over is the fact that these two were being subtracted from the beginning. We still have the subtraction left over, so we're going to have R2 minus now RT. And then of course you can imagine what 1 times this would be. Okay, so now I'm going to start writing this out. We have R1 equals, and since we had 1 times that, it's just going to be the RT times R2, and of course we're going to have that over the R2 minus RT. And we wanted to solve for R1, so we get the final answer there. Okay, so I know what you're probably thinking now. I wish we could do that same problem in a different way. Okay, so don't you worry. We have the same thing. We're solving for R1. What is a different method that we could do to solve for this? And this would be by multiplying everything here by R1, R2, and R total. So now we can see we're going to cancel out R total here, because on the left side we already have R total. What's going to be left over is R1 times R2. Okay, so we have R1 now times R2. That's our new left side. Okay, now solving for the right side, we're going to have 1 over R1, so our R1 is going to cancel there. We cancel this, that's going to give us R2 times RT left over. So R2, RT, plus, since we're doing addition, we're going to keep that addition here, okay? That was originally 1 over R2, but of course the R2 is now going to cancel out. What we're going to have left is R1 times RT. I'm going to erase that because I'm running out of room. Okay, so what's left over from the R2 being canceled is the R1 times the R total. Now remember, we want R1 isolated. Okay, so now we have a similar circumstance. We have the same variable R1 and R1 on different sides of the equation. Again, we want to bring them onto the same side of the equation. So we're going to want to move 1 to the other side. However, what we have existing here exists as one sort of piece. So we have R1 times R2. if we just got rid of R1 and we instead did minus R1, we'd still have a times RT left over. And that wouldn't make sense just saying R2 times RT times RT now because you got rid of the R1. So you got to keep the R1 and the RT together. And we're going to move both those now on the other side. Okay, now on the left side, we're going to have R1 times R2. And now, since we want to get rid of this T and it's being added to, all that we're going to do is subtract by R1 and RT on the right side. That'll cancel it out. But that's what we get here on the left side. Now we have R1 times R2 minus R1 times R total. Okay, I'm going to have to erase this to get some room, but we already get that's canceled out. That is going to equal still the R2 times the RT. Okay, now we do see, now we created RT on both different sides, but we're not going to think about that at the moment. We're going to focus on isolating R1. Now we did what we wanted to do, and we got R1 on the same side. So let's take advantage of this while we have this circumstance. Again, what we're going to do is we're going to think about R1 being factored out of this equation and then factored back in. If we take R1 out of this equation, we can see we have R2 minus RT, okay? And that's everything is gonna be multiplied now by R1 when we factor the R1 back in. This is gonna equal our R2 times the RT. Okay, but now again, all we want to do is isolate our R1. So we have R1 times this whole thing of R2 minus RT. So again, we could think, now let's divide this entire thing of R2 minus RT, cancel it on this side. Now we divide it by the right side, giving us the total answer of R1 is equal to R2 times the R total over R2 minus the R total. And that is our final answer. So again, if you know how to already solve for resistors and parallel circuits, that just seems kind of ridiculous. And in real life, you wouldn't take all of this time to recreate a new formula. But this gives light and insight into how we can rearrange different formulas. Okay, so it's still a good lesson. And if for some circumstance this formula works out, now we know that we can figure out R1 by taking R2 times RT over R2 minus RT. So I mean, it's not that hard to remember, but I mean, as you know, the whole point is basically so you can take one equation and not memorize a bunch. Okay, so that's what you should get out of this. One of the main uses for this is going to be memorizing one formula and then building many formulas off of that. For example, a voltage drop formula in electrical theory, or what we saw with certain examples with it applying to physics. So we can see this has a broad range, and it's the simple fact of just changing the subject of a formula, or what some might call rearranging a formula. But the point is you're changing the subject. We started off with 1 over RT was basically the subject. Now we have R1 as the subject. Okay, next question. This is the formula for a satellite that's orbiting the planet. V stands for the velocity, the G is a constant, the M is the mass of the planet, and the R is like the orbital radius. It is the distance between the satellite and the center of the planet. Okay, we're trying to find M here. And when you look at any formula and you see V equals the square root of blah, 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 whatever it is, you see the square root. You want to get rid of it. How do you get rid of a square root? Okay, think about how we got rid of the square. We did the square root to cancel it. So like the opposite of a square root, we're going to square it. Okay, so we're going to do the power of 2 multiplied by all this. That's going to get rid of the square root on this side. But what that's going to do is add the square on the other side. Okay, so now we have V squared equals GM over R. Okay, so we look on the right side, we see G and M are being divided by R. So to cancel out that, we could just get rid of the R and do times R. And we times R to the other side. Now I'm just going to rewrite this with the GM starting on the left side since we want the M. So now we have GM isolated equals R times voltage squared. Okay, now simply we want to isolate the M, and again, G and M could be written in any order. It's just multiplying. It could be M times G. So with that in mind, we can get rid of the G by dividing by G to both sides, and it's perfectly plausible. Now we have the formula of M equals RV squared over G. And that is our final answer there. Okay, next question, we have the period of a pendulum. The period of a pendulum is equal to 2 pi times the square root of L over G. In this circumstance, we want to solve for G. Of course, we're looking at the square root. I said the first thing when you see a square root is you want to get rid of it. We could get rid of it by squaring both sides. We could do that now, or we could do it later. In this circumstance, we're just going to first get rid of the 2 pi. How we're going to get rid of the 2 pi is we're going to look at the circumstance it's in. 2 pi times the square root of L over G. So to get rid of it, we're going to divide by 2 pi, okay? And that cancels out on the right side there. And on the left side, we have T over 2 pi. Now that's equal to the square root of L over G. Now at this point, we're going to do the square to both sides, canceling out the square root here on the right side. Now rewriting it with LG starting on the left side, we're going to have the square root cancel. So we're just going to have L over G, and that's going to equal now our T over 2 pi. And of course, it's all going to be squared. So it's not just the T being squared, it's the T and the 2 pi. So we want both of them. And again, we could think about expanding this. So we're going to have the square times the 2 and also the square times the 2 pi. Now what that's going to give us is LG equals T squared over 4. Okay, and it's not just 4 pi, it's 4 pi squared, because we're going to square everything, okay? We're squaring the T, the 2, and the pi, okay? Okay, now there should be sort of an alarm going off in your head, and it's fine if not, but you really need to solidify this, is that when you see two fractions, you want to cross multiply, okay? Because this will be really weird. You have L over G, and then you have all of this stuff that is being squared, and again, with L being over G and wanting to isolate G, well, you're not probably going to want to move G onto the next side and add a bunch of horror there. You probably don't want to add more to the left side, especially, I mean, you already have a fraction, you have pi, you have stuff being squared, okay? Just always remember the cross multiplication. Okay, so we're going to do the L times the 4 pi squared and the G times the T squared. I'll just write that up here. That's going to equal L times 4 pi squared. That is going to be equal to G times T squared. Now we want to isolate G, so we could simply divide by T squared to get rid of T squared here on the right side. Now we have divided by T squared on the left side, which gives us the answer of G, now written on the left side here, equals L times 4 pi squared over our T squared. Okay, and that is our final answer. If you're curious, the G is going to represent the gravitational acceleration. Okay, the next question, we're looking at the electric force between two charged particles. We have the constant of K times Q1 times Q2, which is the magnitude of the two different charges, divided by R squared, which is the distance between the center of the two electric charges. And we are solving for R. Okay, similar thing, we have everything on the top divided by R squared on the bottom. To get rid of R squared on the bottom, we could simply do times R squared, canceling out the bottom there, and then of course, doing it to the next side. Now on the left side, we have F times the R squared is now equal to the leftover K, Q1, and Q2. Okay, now to further isolate the R, we could just think of getting rid of the F since we see the F and the R are multiplying, again, they could be flipped. It could be R times F. So we could just divide by F. Of course, now we're going to have to divide the other side by F2. Now we have R squared equals the K Q1 Q2 divided by F. Now again, we just want to isolate R. So how are we going to cancel out the square? We're going to do a square root. Of course, that's going to cancel out everything on the left side there. So we're just going to now have R left over, which gives us the answer of R equals the square root of K times Q1 times Q2 over F. Okay, and since because the fraction kind of made that go down, I'll rewrite that so you can actually see it's, yes, the whole thing is to the square root. Okay, so here is the final answer, and this is the final answer to the final question. So it's the end of this video. If you did enjoy this video, please give it a thumbs up. Other people can see it and they can also get help from it as well. If you want to see more videos on electrical theory, make sure to subscribe. Of course, this video wasn't really about electrical very much, but this is going to be a topic that's going to tie into a lot of my other videos coming out now. Just like my music theory YouTube channel, my videos on here are going to be posted in chronological order for the most part, to where if you watch what I post from the beginning to later on, each video is going to build on each other, starting off simple and then getting more complex. With electrical, there's so many topics though that I am going to be going off to many different topics, but we are going to be tying everything together at some point, and it'll become very complex. But it'll be very complex in a comprehensible way, since we've dealt with all the stuff that makes the thing complete in little isolated ways. So be sure to check out my next video, which is going to be all about voltage drop calculations. To make sure you don't miss any videos, hit the bell icon and you'll be notified every time I upload a video. Till next time, take care, goodbye.